people talk about sight and seeing something, they are talking about visual perception, but most of the time they describe visual sensation or the stimulation, often leaving out the perception part. Traditional approaches describe how we sense height, width, depth, shape, motion, and colour of the world around us. The light going straight into our eyes from light sources and bouncing off surfaces into our eyes. Cells in our eyes then creating a retinal image for our brain to correct, interpret, because visible light is an energy that doesn't carry with it the number of height or number of width or any of those other properties. We don't actually have a chair recreated in the retinal image. Those properties aren't the same. They can't be the same. That is where our brain, or often called our central executive, fixes the bad copy because the stimulation, the things we sensed, isn't good enough. The stimulation is impoverished. However, the ecological approach to visual perception, ecological optics, suggests we don't need to perceive those properties, the lower order variables, because we perceive the relationship between us, the organism, and our environment. Perceiving higher order variables referred to as affordances. The light reflecting, mirroring, and being absorbed in the environment is structured. All the light travels in a unique way, making it structured by its interactions with objects, like me and my wall, but is also distributed within space, referred to as an array. And so ecological optics describes how structured light in the ambient, surrounding, optic, light, array, distribution helps us move. Ambient optic array, the surrounding light distribution. But we also have different heights, and animals have different capabilities to detect energy. So the observer also adds uniqueness to the situation as it moves. And as things move, light is structured, adjusting the perception. Which means, instead of asking, how does the light going into our eyes get fixed by our brain to help us perceive the world, ecological optics asks, how does light get used by our muscles to move? This is another example of how the ecological approach asks different questions, resulting in different tests, methods, analysis, and results. There is no mention of rod or cone cells and no mention of fixing an image. Instead, organisms encounter the ambient optic array and are sensitive to the changes. This requires a visual system, but no particular system, which I will expand on later, but the structured light provides information about surface layouts. Bumpy surfaces will structure light differently to smooth surfaces. Vertical, different from horizontal. And continuous, different from two joined surfaces, because obviously there's a gap. Then some surfaces will block or occlude other surfaces with the edge, the occluding edge of a surface. Explanations from Euclidean geometry and Newtonian mathematics will often describe an object's depth and space, the objects existing in depth and in space. But objects don't have depth or have space. It can't be measured. A hole might have depth, and a room might have space. But the words describe an absence of objects. Instead of depth perception, the ecological approach would suggest we perceive distance across objects, or perceiving the surface layout, the optical texture of surfaces interacting with visible light. If we look at the checkerboard pattern, the first vertical pattern has minimal differences. The squares look the same. The second and third appear slanted with systematic differences depending on how slanted they are. The squares changing shape as you go up the image. Then the final image shows drop-offs between surfaces, creating dramatic differences. How quickly the optical texture changes is information about the steepness. One of the most famous studies in visual perception research used this checkerboard pattern with babies. The visual CLIS studies have babies on see-through plastic, plexiglass, and underneath is the checkerboard pattern, but with a cliff edge. Half is shallow, and the other half is deep. It is all safe, but babies were put on the shallow side to see if they would crawl over the cliff edge. They wouldn't actually fall, but it could look like it. What they found is that the younger babies crawled straight over it, whereas the older ones didn't. Historically, this was given as evidence that they had learned depth perception. But as research continued, it isn't age, but crawling experience. It's not depth perception or fear of heights that stop them from crawling, but the ability to perceive surface layout. Surfaces can be crawled on, depth can't. Early crawlers haven't learned much about texture drop-off, so they crawl right over the cliff. Experienced crawlers have learned about drop-offs, so they avoid the cliff until they learn it is safe. Developing perceiving and acting abilities is something I will talk on in future videos, so subscribe if you don't want to miss that. But organisms or animals detecting this visible light have relationship with it. Taller people relating differently to shorter people. Sitting down or standing up, the structured light is body scaled. Each point of observation is different, which changes the study of visual perception. Instead of fixing a bad copy of the world, the question is now, how do organisms detect those patterns of energy? Visible light in this case. We are nearly always moving, so the patterns are nearly always changing. Those pattern changes in structured light are referred to as optic flow. I'm going to emphasize flow there because it's not putting images together one after the other, but experiencing a continuously unfolding optical event, a continuous flow. This optic flow informs how the organism, animal, is moving in relation to the surface layout, where it is going, and when it is going to get to its destination. But its mass, strength, dexterity, and skill of how it moves through the world, and how it moves things in the world, will change that optic flow. And so optic flow isn't just body scaled, but action scaled. The structured light detected provides information about not only the surface layout, but the relationship of the organism to the layout of the surrounding surfaces. Or in other words, the affordances of those surfaces for the organism, animal. But when we continue with visual perception through motion, more questions come up from traditional explanations. If we are seeing a picture after a picture, like a camera, and the brain needs to interpret each image, how does it know the difference between an object moving left to right, or the head, eyes, moving left to right? If the image is blurred, how does the brain interpret the surface as smooth? Motion creating a problem for visual perception explanations, much like depth and space do, and for similar reasons. Objects don't have motion. Motion isn't a property, but an abstract concept. And with obviously stationary objects, motion doesn't exist, but the objects can still be seen. So motion is relative to the perceiver and the movement of the perceiver. If we think about a ball being dropped, there is motion, there is optic flow, but the optic flow is localized around the object, the ball. As the ball falls, the bottom edge is hiding or occluding surfaces behind it, and the top edge is revealing surfaces behind it. If it was to be thrown at me, the ball would look bigger as it got closer to me, the entire outer edge of the ball occluding the surfaces behind it. And so if I wanted to catch the ball, you might say I would need to guess where it is going, or calculate, predict the destination. My face. But what if information about the time to arrival is in the localized optic flow? How quickly the ball occludes the background relative to the current occluded background, from there to there. This relative rate of expansion, the ball occluding surfaces behind it, is called tau. Information about time to arrival, assuming the conditions stay the same, of course, and nothing impacts the ball mid-flight. But if the ball is missing me, the expansion and occlusion of surfaces will be different. One side getting larger than the other, because it's smaller, and asymmetric differences in occluded surfaces, that side more than this side. But then we can also move. If I were running towards the ball, my field of view will be changing. I can only see structured light in front of me, the optic flow, and as I move, the entire optic flow changes. The global optic flow changes. Walking and running have different rates, and again, tau is information about time to arrival, which is information about my speed of movement. Again, assuming conditions are the same and nothing gets in the way. So to get into the right position to catch a ball, I could do unconscious calculations using geometry and math, or I could use information about the optic flow in the ambient optic array. All I need to do if the ball is thrown at me from somewhere is follow two simple things. move so the ball appears to be travelling in a straight line, and stop running when the ball is and stays directly overhead. Looking at a thrown ball from the side, it's like a U shape. But when catching a ball, it is in a straight line. If you are slightly to the right or slightly to the left, you'll be able to start to see that upside down U shape. Moving forwards or backwards will move the ball up or down that line until you are directly underneath it, in which case it's going to be getting bigger and bigger, like when the ball was coming straight at my face. It's going to come bigger in a symmetrical way. If I'm slightly to the left or slightly to the right, it will appear bigger or smaller in an asymmetric way, because it's going to miss me. This was tested in the mid-1990s using video cameras and a ball being thrown 50 metres or 164 feet. But what is significant here is that the information is not in the retina, not in the retinal image, not in the brain, not a fixed image or calculated through models of the world. Nor does this require any particular visual system, be that chambered eyes, compound eyes, visual light, or infrared. It only requires a visual system to be sufficiently sensitive to detect changes in the optical structure, ambient optic array. So this explanation could, should, and does work beyond humans. Similar studies to the ball catching study has been done with dogs, catching frisbees at 10 to 20 metres or 32 to 65 feet. Gannets and seabirds dive into water for fish from 30 metres, nearly 100 feet in the air, reaching speeds of 100 kilometres an hour, over 60 miles an hour. And they need to keep their wings out to steer towards the moving target, but they have to close them in time before they hit the water. So how do they know when? It could be they use height, velocity, and acceleration to consistently calculate those answers each millisecond for adjustments, or they use information from the optic flow. Then, if you didn't know, bees do a little dance when they have found nectar. They do a different dance depending on the distance it is from the hive. Bees could use an estimate of energy used to calculate a distance, or they could use global optic flow. A study on bees looked at what would happen if they flew through different tunnels to a hive 35 metres away. The tunnels were the first 6 metres of the 35-metre journey. One tunnel had a black line going straight through it, but the other tunnel had black rings going around on the inside. Bees that went through the ring tunnel were more likely to signal the nectar as further away. Why? The idea is that the ring tunnel generated more global optic flow, more changes, suggesting bees used the rate of optic flow to determine distance, not energy consumption, because straight line, limited changes. But if we consider local and global optic flow as a way to detect information from light energy, we still have an issue. We move. The optical information will also need to provide information about the organism's ability to do the thing, information about the effort or work required. It should be action scaled with information about energy required, just like the higher order variables the ecological approach suggests we perceive. Affordances, which I discussed more in this video over here.